Yeah, thank you for the introduction. Thank you for the invitation. I'm very happy to be here. It's my second time in India, and the second time, the trip to India is basically visiting ICTS and taking a route from the airport to here and back. What I want to talk about is based on a paper that appeared today with my PhD student Fabio Ori and Alex Cervantes, who was a postdoc here at ICTS a few years back and currently is with us at Ghent. And let me start with an introduction. So we started thinking about whatever I want to tell you because of sharp geometric probes of the bulk in ADS-CFT. So let me just go very quickly about it because the room is filled with experts in this area. Holography encodes gravity in the language of boundary quantum field theories. And what we know about the bulk ultimately, what we know for sure about the bulk ultimately stems from the equality of partition functions, so to speak. And this gives us a direct access to correlation functions, thermodynamics, and entropies. And while all these quantities, by definition, are geometric, they're only sometimes sharp in the bulk. And by sharp, I mean, for example, when we consider a correlation function of two heavy operators, it's going to be approximated as an exponent of the proper length, so like a geodesic, proper length of the geodesic that is spanned by the insertion points on the boundary, or sharp is also entanglement entropy, and you can make it even sharper with things like kinematic space, etc., etc. There are also bottom-up sharp geometric objects like holographic complexity. And the problem with them, or the feature of them, is that in the vast majority of cases, they are at best only qualitatively understood. And overall, nevertheless, we like such sharp quantities because due to their localized nature in the bulk, they allow to directly probe black hole regions of interest, for example, horizon, interior, and perhaps singularity as well. And if they are top-down in principle, we could calculate them independently on the boundary. And if there's a match between this boundary calculation and the bulk, then we have an indication that the bulk geometry works. So that's sort of the power of these approaches. And what I want to discuss today goes under the name of Timelike entanglement entropy, more precisely holographic timelike entanglement entropy. And this is due to a brilliant paper by the Kyoto group, in particular by Jonathan, who's sitting there at the back. And the idea that this group of researchers pursued is the following. So we have this picture of entanglement entropy in which we have a subregion on the boundary of ADS that lives on some constant time slice. It's a spatial subregion. And then we have a Takayanagi or HRT surface that stands from the boundary of the subregion on the boundary. But then what we can do is we can sort of turn the table and ask a question: what happens if we consider such a subregion, but now extending along a timelike direction? So if you think about ADS-3 holography for definiteness, I mean, this is the setting of this picture. The spatial subregion for the standard entanglement entropy, the paradigmatic one, is going to be a single interval on some constant time slice, whereas the timelike subregion of interest in the context of this holographic timelike entanglement entropy is going to be a timelike interval that, for example, is located at some spatial position on the boundary of ADS. And of course, the question that this raises is if this kind of an object leaves an imprint on the bulk in the form of a sharp quantity in the way I defined them earlier on my slides. And of course, we'll be interested in connection between covariant quantities defined by such a subregion on the boundary and quantum information measures in the spirit of the workshop. And while you might be pessimistic about such a connection, it turns out that you perhaps should not be. And the reason is that such objects, which are sort of like time-like bipartitions of the system, appeared earlier in the literature of tensor networks in the context of Lorentzian time evolution. So this is a tensor network representation of Lorentzian of just time evolution in a quantum many-body system. So we have some operator insertion. We have like two unitaries that evolve us forward in time, and we have an initial state with which we contracted. This initial state has a form of MPS tensor network, and time evolution can be represented, for example, in terms of TEBD algorithm. And then there was a brilliant idea by this group 15 years ago to come up with intelligent way of contracting this tensor network. So sort of like instead of contracting it in a brute force way, like this, like absorbing this layer into the state, that layer into the state, and so on and so forth, what these people came up with is to fold this tensor network and then contracted it along the spatial direction. So instead of contracting like this, contract it like that. And when you contract it like this, in the end, the final step in this contraction is basically an overlap between two fiducial states, the left state and the right state. And each of these states have also a form of a matrix product state, but now these states extend in the time direction. So this is sort of like a temporal MPS state. Of course, when you have such a setting, what you can do is you can apply standard tools from quantum many-body systems, from tensor networks, and you can bipartition this final product and calculate for Neumann entropies either of the left state or of the right of some subsystem of the left state, time-like subsystem of the left state, time-like subsystem of the right state, or perhaps something like this, in which case the relevant density matrix is not going to be necessarily Hermitian. And then like the relevant notion is a pseudo-entropy. So what I'm trying to, yeah. Well, I mean, over here, this picture is powerful when the system is actually infinite in spatial direction. Because I don't understand how you're getting a state L, a pure state L. But this is a fiducial pure state, in a sense that this state just this state, you interpret it not as a state in the original Hilbert space. It's like a state in some auxiliary Hilbert space that extends, for which the lattice sites are sort of like discrete time steps of your evolution. So it's not a state in the original Hilbert space, it's an auxiliary state. But nevertheless, since this is just some matrix, you can calculate the reduced density matrix, generalized reduced density matrix of this object, calculate its von Neumann entropy, and try to ask like what are its properties, how it behaves, etc. So the punchline of this discussion is that while considering subregions in the Timelike in the temporal direction might sound exotic a priori, it's not something that is completely exotic, and it has been thought through to some degree by the tensor network community, and it has concrete applications in this field. So let me come back to the setting of quantum field theory. So one can ask a simple question, if one can implement this kind of a logic in the context of 1+1 dimensional conformal field theories for which we have closed form expression for the entanglement entropy in the vacuum state. So this is the famous formula where C is the central charge of a given CFT, and x1 minus x2 is the extent of the interval. And of course, what one can do is one can attempt naive analytic continuation. This was proposed in the original references in this area. And when you analytically continue the interval to extend in the time direction, what you do is like you acquire a minus sign over here, and this minus sign spits out for you an imaginary part for this quantity. So that's sort of an expectation of how would temporal entanglement entropy look like in a conformal field theory. And of course, one thing that you can do is you can try to let me finish the sentence. Like one thing that you can do is you can try to consider a tensor network representing a critical system, and you can ask, if you can match it with this kind of a calculation. And Luca Tagliacozzo and collaborators in the recent paper have made steps in this direction. So there is a concrete connections with tensor networks. But there was a question from the audience. Yeah, that is fine. Okay. So what connects this story of entanglement and analytic continuations with holography is this very suggestive picture that comes from the original references that started this discussion, which is, can we interpret this temporal entanglement entropy holographically as an object living in a dual geometry? So what this group pursued is a very beautiful idea, ultimately, which is the following. So if we think about the proper distance in ADS, we work under conventions that when we calculate a proper distance between two spatially separated points, it's going to be some real non-negative number. But now, of course, if we follow the same convention and we ask a question, what is the distance between two time-like separated points, the answer is going to be complex because we're going to be integrating something with a minus sign under the square root. So if you follow this logic, then what you might be tempted to say is that perhaps the counterpart of the real part of this temporal entanglement entropy in a CFT would come from a real spatial geodesic, whereas like the imaginary part would come from a time-like geodesic. And indeed, these authors found a configuration of geodesic segments that explains this combination. And it consists from a standard spatial geodesic that extends from the boundary of ADS to the Poincare horizon, to the future and to the past. And then there is a time-like segment that connects them, that extends between the past Poincare horizon and the future Poincare horizon. And if you combine the answers, then you get precisely this value. The problem with this approach is that this does not really tell you what to do in more complicated cases. So, for example, if you look at higher dimensional cases, excited states, it's a priori completely unclear how to obtain an answer for a tentative candidate answer for holographic time-like entanglement entropy. So the goal of this work that appear on the arXiv today is to work towards the prescription for calculating holographic time-like entanglement entropy, in particular reproducing this answer and applying it beyond ADS3 CFT2, which is like the simplest setting that you can think of. So that's a good breaking point, and check with you if there are any questions, comments.
In the original tensor network setup that you mentioned, was there also a real and imaginary part for this quantity?
Yes, like these matrices. In this case, like this matrix is going to be in this case, like you're going to end up with Hermitian matrices, so you're going to get like just a real answer for fundamental entropy. But in this case, you're going to get a generically complex answer. Mm-hmm. So you're going to have a real part and imaginary part.
Okay.
Yeah. Of course. So let me come back to this, because I will have something to say about this. In particular, what we would like is to have a prescription in which Poincare horizon does not necessarily play any prominent role, in a sense that like you just try to seek for the surface, you get it, and then you try to interpret it. And if it touches a Poincare horizon, good. If it doesn't, who cares, right? Okay, thank you. Yes.
So do you want to identify this tensor network picture to this holographic picture? Is that what you said? It seems that the tensor network picture is manifestly Lorentzian, while this this time-like entanglement entropy is like using weak rotation. So essentially, it's Euclidean first. So it seems two are different.
Well, let me keep going, and we can come back to the discussion. But I think it's an important point that's going to be even more important when you see what I have to say. Okay, thank you. So let me state the proposal. Actually, it's not really the final proposal. It's like a version 1 of the proposal. So the idea would be that holographic time-like entanglement entropy is going to be given by Bekenstein-Hawking entropy of a complex boundary anchored extremal surface of codimension 2. So this complex is a key word, what we're going to do is we're going to allow this extremal surface to penetrate analytic continuation of the bulk spacetime, in a sense that I'm going to make clear on the next slides. So, of course, I want to come back to the motivation. So, it seems, based on the definition, that this holographic timeline entanglement entropy, it has a chance of becoming a sharp probe of the bulk, as we would like it to be, with some caveats, the caveat being that it's going to be a sharp probe of the complexified bulk. So let me discuss the proposal in the example of this picture that we already drew. So extremal surface means that we extremize the surface function no matter what. Complex is a bit subtle because complex metric appear in the discussion of gravity in various ways. But for us, the complex surface means simply that the surface lives in the bulk metric in which the coordinates are complexified. So in particular, we can take, say, a Poincare-Patch ADS metric. And in this Poincare-Patch ADS metric, we say that, say, the radial direction is no longer just non-negative variable, but actually it's a complex variable. And similarly, all the spatial and time direction are also complex variables. And boundary anchored means that the surface satisfies real boundary conditions. So that, whereas like we allow the surface to extend into the complex bulk, we wanted to satisfy the standard boundary condition on the standard boundary of ADS that is present for real value of the radius as it approaches 0. So, for example, in the context of ADS3 in Poincare-Patch, we want the surface to terminate at some real values of times that are distinct, right? Like we want to have some extending time and real values of z that are very small, right? This epsilon is the UV cutoff that is going to be real, and we're going to be taking this UV cutoff to 0. And of course, by construction, the surface is not going to move in the remaining spatial direction in this case. So now, it turns out that you can find a solution as a complex extremal surface to the problem of a single interval in empty ADS in Poincare-Patch, which comes back to your question. And the solution is quite peculiar, which is that you can view it in the following way. So there's going to be we're going to parameterize the solution in terms of the affine parameter. So the affine parameter, like the length of this quantity, we know that in order to match it with analytic continuation of entanglement entropy, the length has to be complex. So the affine parameter is the total span of the affine parameter it has to be a complex number. So what we draw here is a complex plane of affine parameter, drew in a convention that the affine parameter starts at minus something and ends on the plus something, in such a way that the total length of the curve, total length of this extremal surface of geodesy in this case, is just 2 lambda star. And now, in principle, you can imagine that you can take various paths in this complex affine parameter plane. But if you take the solution and you view the solution along this particular path that I drew here, which is first you start with the minus lambda star and you move along a constant imaginary part towards the 0 value of the real part. Then you move along this segment and you move forward to the final boundary condition over here. Then you can interpret this path in the following way. The blue parts are just geodesic segments in the original ADS3 spacetime that indeed connect the asymptotic boundary with the Poincare horizon as was interpreted in the original paper. And then there is something very funny happening, which is that they continue onto the complex plane, but now they don't continue in the original ADS spacetime, but instead they continued in an complexified version of ADS spacetime in which both the z and t direction are purely imaginary. But you know that ADS spacetime has this isometry. So ADS spacetime in Poincare-Patch is going to have the form dz squared plus, dz squared minus dt squared over z squared. So there's this isometry in which you can multiply everything by some constant, right? Let's call this constant for lack of better name kappa, right? And this kappa cancels, right? So if we pick this kappa to be I, so normally you're not supposed to do this, right? If you were to do this at your holography exam, probably that would raise some suspicion. But what I'm trying to say is that while this geodesic continues its motion in the complexified ADS space, this part of the motion you can nevertheless view in some sense as the motion standard Lorentzian metric. But you have to bear in mind that the standard Lorentzian metric is the one in which you introduce an I in front of all of the coordinates. Yes. Well, I'm not sure if you should assume that you're gonna be continuing this, right? Well, I think yeah. I mean, I see your point. I mean, I'm not sure if I have like a very crisp answer to this. I think the subtlety here might be that it sort of reaches infinity, and then it does something funky. Well, I'm just trying to interpret it in the language of these particular coordinates. Yeah, I mean, of course, like you bring up like I feel like the question that one should be asking is like if one thinks about complexification of the Poincare horizon ADS, is it going to be the same as complexification of the global coordinates? Yes. Yeah. Also, you're asking like if one could think about the red one as actually continuation of the space-like. That's sort of a question. I mean, there is something of this. There is something of this sort happening here, which is that normally you cannot really connect a time-like geodesic to a space-like geodesic, right? Because otherwise, like, would be just going normally time-like and then suddenly turning space-like. That's not going to happen. So, like this factor of an I here is crucially needed in order to ensure continuity of the momentum along the geodesic as it turns time-like, right? That's sort of what's going on. But there's a thing that goes against this intuition that you have, which is that if you calculate the total proper length, then the total proper length is going to be complex. It's going to have a real part and imaginary part. Whereas, like if you were to do what you want to do, then you would like to get a total real length, real positive length. Yeah. I mean, it's a good point that you made. Yeah. There's nothing special about it. I mean, like I just drew it that way because I wanted to make a contact with the original interpretation of this quantity. And what I'm trying to say is that within this paradigm of complex extremal surfaces, there is a picture that looks very similar to the original argued picture with subtleties. But this brings me to this is the picture that was originally advocated. But this brings me to this slide in which basically the lesson is that, of course, we can take different paths in the complex affine parameter plane. And then like the path that is drawn over here is just like a very particular path that you can consider, but nobody forces this upon you. In the same sense in which when you do integration in complex analysis, nobody really tells you to integrate along the real axis, right? And we very often do this by deforming the contour, yielding nevertheless the same answer, right? Well, for a point, I mean, I don't know. I mean, it's a exploratory study. We're going to be dealing with situations in which you can do this, right? But this problem that you're raising is a problem that affects also other things. So, for example, like in the context of probing black hole singularity, like complex geodesics play a prominent role as the dominant saddles in a paper from 2004 or so. So all these issues that you're raising appear also there. So I think like the take home from this is that this is an issue that one should think about more broadly. So the take-home message from this analysis is that there's going to be various paths in this complex affine parameter plane that one can take, and only some paths can have an interpretation as geodesics propagating in sections of real manifolds. In general, a generic path is going to have an interpretation as a motion in genuinely complex metric. And this is a very simple setup. And perhaps like the simplicity of the setup imposes upon us this possibility of interpreting this in a quite a standard way. In more complicated setup, we don't have this picture. Everything is genuinely complex. But from the point of view of the answer, it does not really matter. Any equivalent path is good. So in particular, if you come back to the standard entanglement entropy, for standard entanglement entropy, you can also take a complexified parameter along the curve in such a way that the Takayanagi or HRT surface lives in complexified bulk, but then the length of it is going to be real and non-negative, and also like you're going to be able to interpret it as well as living in a Lorentzian or Euclidean spacetime. So this was the basic sanity cross-check. Now we want to make a prediction. And by making a prediction, we want to look at something where you don't have a closed form expression for holographic entanglement entropy that you can analytically continue. So what we're going to be looking at is a timelike strip in the ADS4 black brane spacetime. So the surface before was a geodesic, now is going to be a two-dimensional surface. It's always a codimension 2. So the setup that we have on the asymptotic boundary is we have time, we have one spatial direction, we have another spatial direction, and we're going to be considering boundary condition in which our entangling region extends in time for a duration of delta t. It's localized in one spatial direction, which we called x-perp, and it extends over another spatial direction that we call x-parallel. And now if you were to draw what happens at the bulk, in the bulk, it's going to be, roughly speaking, the following picture. So there's going to be translational invariance along this parallel direction. That's enforced by the boundary condition, which is this translational invariant strip. And then the surface is a complex surface that extends into the complex bulk. And what I wanted to signal is that it starts in the real section of the manifold, but now as it goes inwards, it acquires, I mean, the value of z acquires an imaginary part. So then it starts probing the complexification of the black hole spacetime. And the metric, of course, is the planar black hole metric in ADS4 with the horizon located at ZH. And what's important is that because these are extremal surfaces, a lot of the things that you learn in the context of entanglement entropy, in particular in highly symmetric setups, the presence of a tip, also go through. Similarly, another aspect of entanglement entropy surfaces, which is the presence of possibly a critical surface, which also happens for the volume complexity, is also true in this case. So what I'm plotting here on this diagram is a position of the tip of the surface as a parametric plot with respect to the separation on the boundary condition. So over here, we have to solve the problem numerically. So we're doing numerical computation. We're solving these ODEs in ADS4 black brane spacetime. And it turns out that in this case, there are two branches of solutions that appear in black hole geometry. So that's a novelty with respect to the previous case where we only had like one solution that we could have parameterized in terms of various paths in the complex affine parameter. Over here, we have two distinct branches of solutions. So one, yeah, of course.
I mean, again, why in the previous case, I thought like in the previous case, the geodesics, like these curves are extremized piecewise. But like in this case, you are extremizing not like a piecewise, but the just.
Very good. So thank you for the question. So over here, the point I wanted to make is that there is this piecewise path that acquires interpretation in terms of motion in effectively real geometries. But you don't have to consider this path in a sense that you can consider any path, for example, a path that goes like this. And this path is going to give you the same answer. So in a sense, like trying to seek for such paths might be like a bit of a red herring. And instead you can consider like just any path that does the job, in particular the one that is convenient for you.
And for this case, if you consider some other path which is still extremal, this gives you the same answer?
The length is going to be the same because for affine parameter, right? Like, I mean, like for this path, the length of this path is going to be just a difference between the endpoint,
okay.
the starting point, which is 2 lambda star,
Ah.
and then what path you take, it's not going to matter, right?
I see.
So over here we say let's pick a path let's pick a parameterization of the surface that's just convenient for us, and it happens to be that in this case we consider the parameter on the surface to be z, and then let's roll with it. But we could have chosen alternative, and I think we chosen alternatives to cross-check our results, and the results are not dependent on it as they should.
I see. Thank you.
Jan has a question.
Yeah, can you clarify exactly what the prescription is? So we complexify the metric. So we now say we do A-3, so you have a 3-dimensional complex metric.
Yeah.
We have a 1-dimensional curve in this, a real curve in this 3-dimensional complex metric, and now we look for any 2 surface that ends on this curve that extremizes the area functional analytically continue to the complex spacetime.
Yes, this is what we're doing here, and we want to see what are the consequences.
Yeah, and there's the final result will be highly ambiguous because analytic deformations of the extremum leave the action invariant, so there's not a unique outcome. But the other question was the square root that you have in this action, in principle, it has branch cuts. So you have to tell me how you go around the branch cuts and so on. And so there's some interesting topological question also. How do you deal with that?
Yeah, so regarding the first question, what I want to signal is that this kind of, I mean, you can think about like various paths in this complex lambda plane as independent surfaces naively, but we don't like to think about it that way. We think that these are like just various representations of the same surface, and we should just pick one that is convenient for us. So similarly, if you were to play the same logic for Takayanagi or HRT, then you can try to seek for a surface that has an interpretation as a surface in a real spacetime, and complexify the affine parameter along the surface, right? And it's going to suddenly start extending the complex bulk directions. And from this perspective, any choice of the affine parameter path is going to be equally good, right? So that's one thing that we want to. That's one aspect of your question. And now, like I see that I have 5 minutes, so maybe we can talk about the other aspect in private after my talk. Okay. So let me discuss in the remaining few minutes like this black hole case. The punchline here is that there are now competing extremal surfaces in the sense that there are several solutions. There are 2 classes of solutions satisfying boundary conditions, and these solutions, as I said, like we call the vacuum connected ones and vacuum disconnected ones. These solutions come in pairs in this case that are related to each other by complex conjugation. So that's why we have like one part of the branch, the other part of the branch that are Z2 symmetric regarding this axis. And now this vacuum connected branch is called like this because as the separation on the boundary goes to 0, the tip of the surface approaches the asymptotic boundary, right? So like it does whatever we want it to do from the point of view of the UV-IR correspondence. It does not extend significantly into the bulk when the separation on the boundary is very small. And then when you make the separation larger and larger, it turns out that there are critical solutions that are solutions that have so these are like extremal surfaces that extend along the constant Z direction in this case. And this critical, what happens is that as you increase the time separation of your strip, so time extent of your strip, what happens is that at very large separation, you start aligning along the critical solution, as you do for entanglement entropy. And this will be the contribution at very large separations. But now there is this branch of solutions that we call vacuum disconnected branch, and this comes from the existence of that critical point. So when the separation on the boundary is very large, they align along the part of the spacetime associated with this critical point. But the funny and confusing aspect of it is that as the separation goes to 0, it turns out that these solutions start probing singularity of the complexified black hole metric. So they manifestly violate UV-IR correspondence because these surfaces are spanned on extremely short interval, but nevertheless they manage to extend sort of infinitely or very far away into the bulk. So these are exotic, well, you might think exotic solutions that appear in this case. And then the question is, within this prescription, what would be the analogous conditions to the conditions that you impose on Takayanagi surfaces that you select the physical one when there are multiple contributing, right? And the answer to this question is that we are not yet sure, but we can entertain several possibilities. So the possibility A is gonna be that we're gonna pick a surface with the minimal real value of the proper area. So that's a very natural thing to do. But now, when you do this, it turns out that at short separation, so for very short time extent of the strip, the solution that dominates, according to this criterion, is gonna be the one that probes black hole singularity. And then only at larger separations, it's gonna give way to the solution that does not do so. So if one utilizes this kind of a condition to select among multiple extremal surfaces, then what one does is one violates UV-IR correspondence. So a possible caveat is that the UV-IR correspondence was formulated in the context of real spacetimes. Over here, we talk about complexification of spacetime. So perhaps one should not apply it directly. So there is a second possibility that one may want to adopt. And this possibility is that we would like this holographic timeline entanglement entropy to be still given by a complex boundary anchor extremal surface, but we would like to require that it reduces to entanglement entropy upon analytic continuation. And if one imposes this condition, that at short time intervals on the boundary, we are basically probing the vacuum space, the physics of the vacuum, not the physics of the thermal state. And then the relevant solution, then what one would like to pick is the blue one. And the interesting question that one has is that if there is a physical interpretation of the remaining saddles, like we have always like two solutions in this case, two classes of solutions, and then if we pick one, there is also the other one, and one can ask a question if this other one can have an interpretation in a similar way in which the non-extremal but non-minimal geodesics have an interpretation in terms of entwinement in the context of ADS3 CFT2. But of course, we don't know it. So since I don't have time, let me just mention that you can roll with it and you can try to apply this kind of considerations to the Vedia spacetime. So you can apply it to a strongly time-dependent situations. And you can find predictions. I don't have time to discuss them. I just want to signal that this is a reasonable thing to do in the spacetime, and the answers also look reasonable from the point of view of what you expect physically. And to summarize, what we did is we built upon the paper by Jonathan and company and postulated that holographic timeline entanglement entropy acquires a natural bulk interpretation in terms of complex extremal surfaces living in complexified bulk, understood in this particular way. And what I want to signal is that this is a really exploratory study. I mean, it's not that every day you consider living in a complex Z and extending in complex Z. So there are lots of interesting questions to ask. For example, which complex extremal surface to pick when there are multiple ones, trying to derive whatever we postulated in terms of replica trick, trying to understand the subdominant, these contributions that we believe should be treated as subdominant that nevertheless probe black hole singularity, because that's something that is one of the ultimate questions in holography. Try to match the properties with CFT calculations, tensor networks. And moreover, what I want to signal as a final thought is that when we consider geometric probes of the bulk, typically, for good reasons, we we restrict ourselves to real extremal surfaces. But of course, what this shows is that we might have overlooked some important contributions that are naturally complex, in particular ones that might dominate the answer. And this is all that I wanted to share with you. Thank you.
Okay.
So I have a question about the ADS3 when you were describing it. So could you please go back to the diagram where you were drawing to space-like curves with the blue color and
this one?
On the previous one, yeah, kind of that. So what happens if we take the boundary section and the endpoints of the boundary section to the point curve horizon? I mean, the blue curve, just extend the blue curve to the full range. Then there is no space-like curve actually, which is going from the endpoint to the point curve horizon, right?
So there are good. So when you what seems to be happening is that these curves, well, we did this calculation. I mean, I don't remember the all glorious details, but because in this case you have also a closed form expression for the geodesic length, right? You can calculate what's going to be the answer for analytic continuation. And I think what you get is that this imaginary part is going to get some multiples of I2 pi coming from the formula for the geodesic length. So somehow it still works in kind of a similar way, taking into account that sort of the extent on the boundary is larger than what's drawn here. So you can do this calculation, and it's easy to do.
Okay, more questions? So is there some direct connection between the geodesics that appear here and the geodesics which probe the proper time to the black hole singularity? You mentioned in the comments at the end.
So that was sort of like the picture that already appeared in Jonathan's paper, but this is not really the proper curvature singularity in the sense of the curvature like it's a Kretschmann scalar blowing up, because this is the BTZ black hole. And then I think what replaces this notion is going to be this. Mm-hmm. But as I said, like we're a bit torn if this configuration should be picked as a physical contribution at short distances or not. I think this is an interesting question. In particular, one thing that we've been toying with is what happens if you consider other probes in the spirit of the last thought on my slide. And we've been playing also with Wilson loops, trying to see if a Wilson loop in eternal black hole geometry has a power of probing black hole singularity. And I think in one direction, I don't exactly remember now in which one, it seems that it might do the job. So there is some connection between the broad idea of this talk and other probes, but not necessarily in this context, the original work about geodesics.
Okay, great. Thank you. Let's thank Michael again.